Assalamu alaikum warahmatullahi wabarakatuh. Welcome to another computer science lecture for 9618A2, paper 3 advanced theory, and we were doing chapter number 16 system software. Today we are going to start 16.2 translation software. Now this part of chapter number 16 is about how different translation software such as interpreter and compiler works. So first of all, we are going to discuss how interpreters execute a program. Now if you remember, interpreters are those softwares that translate a program line by line. They execute the source code directly. They don't convert it into machine readable format. They just execute it directly, because if they would convert it into machine readable code, then obviously that would produce a permanent exe file. This contrasts with compiler. On the other hand, they create a permanent machine readable file that is commonly known as an executable file or exe file. Interpreters process the program line by line, whereas compilers do it whole program at one time. Now, interpreter translates each line on the go and executes it instantaneously. They detect and report errors as soon as they encounter them, stopping execution as soon as an error is encountered. That's why interpreters are used to pinpoint errors as well, so you know where exactly you have made an error in your code. It allows for efficient testing and modification of small code units or small programs, and that's why it is heavily used in for debugging purposes during development. Since there is no object code produced, the interpreter will need to be used every time the program is executed. After each statement is executed, control is returned to the interpreter so the next line can be checked before execution. This is how an interpreter works. You need a source code, you need error corrections, and you need program input. All three are dealt by interpreter, then either an error message is generated or either you get a program output on your screen. On the other hand, the stages in compilation of a program are as follows. Compiling a high level code into machine code can take many stages that involve lexical analysis, syntax analysis, intermediate code generation, and finally code optimization or simply optimization. So you write your code in a high level language which goes through lexical analyzer, then it goes through syntax analyzer, then it goes through immediate code generation, then the code is optimized, then finally it goes through code generator and a machine code is produced. During all these stages, symbol table as well as error handler are consulted. So first of all, let's talk about lexical analysis. It is the first step in compilation process where the source code is dissected into meaningful symbols which are known as tokens. This process involves scanning the code line by line to categorize parts of the code into tokens. These tokens are the building blocks of the code, as just like words in a language. Tokens can be keywords, they can be identifiers, they can be literals, operators, or any other symbol that have a significant value in that programming language's syntax. For example, int number equals to 10. By the way, that would be something like this is written in Java, or well, basically C# also follows the same thing, same format, but this is from Java if you're interested to know. Anyways, including this as well. The lexical analyzer would break it into words or tokens. This would be one token, this would be second, third, fourth, and fifth. Now these would be recorded into a symbol table. Int would be given a token value, number would be given some other value, equal to would be given some other value, 10 would be given some other value, this semicolon or terminator would be given another value. Now this code, int number equals to 10, can be written like this in terms of the token values from the symbol table. The symbol table and error handler both, that's why both of them are connected to each stage, because they are either created or consulted with during each stage. Challenges in lexical analysis: the lexer must correctly identify tokens when there might be ambiguity, such as in the use of symbols that could have multiple meanings based on context. Although there are very few programming languages that would have such multiple meaning syntaxes or tokens, but still the process must be efficient, as it is the first step in the compilation process. If you make a mistake over here, then well, your whole program is going down the drain. Next is the syntax analysis. This stage is also known as parsing, and it is the stage where the stream of tokens is analyzed to make sure that it conforms to the grammar of the programming languages. Basically, you're trying to see whether there's any syntax errors in the code or not. The parser checks whether the tokens form a grammatically correct sequence or not, known as parsing the tokens. This whole process is known as parsing the tokens. It's like checking if a sentence in a language follows the correct grammatical rules or not. Next phase typically involves building a syntax tree or a parse tree, which visually represents the structure of the code. Now there are two types of parsers, top-down parser and bottom-up parser. Top-down parser starts from the highest level structure of the syntax and work down to the lower level, whereas bottom-up parsers work with individual tokens and build up to the high level structure. So basically, top-down parsers starts working from the input taken by the program, and then they move towards how inputs are being processed and combined together, whereas bottom-up is kind of opposite of it, where you start from what processes, what procedures and functions are being applied, and then at the end you come to the part where you're taking input. Again, this detail is not really needed in your syllabus. I just explained it so you don't get confused. You have a better picture. Then the third stage is intermediate code generation. Now, as you all know, code generation is the process of transforming the parsed source code into a format that can be executed by a machine. That can either be the machine code, or it can have any other intermediate form depending upon what language, what high level language you're using and what IDE you're using. When direct machine code is generated, the compiler generates machine language instructions specific to the target processor's instruction set, because different processors have different instruction sets and you cannot just run any machine code on every processor. For some languages that specifically work on a virtual machine environment, such as Java and Python, both of them supports virtual machines, the code is converted into bytecode or P code or intermediate code. This code is not fully converted, or this is not fully translated into machine code, and it is dynamically translated just in time or on the go or whenever the user tries to run the program. So you write a single piece of code and then you distribute it freely, and whoever downloads it on their system, when they try to run the software, it is immediately translated on time into a machine language that is specifically targeted towards the processor of their own machine. That's how one single software can run on multiple platforms. Configuration and code generation. The generated code must be compatible with CPU architecture and operating system of target machine. This is kind of a concept. This is where the concept of partial compilation and partial interpretation comes along as well. Effective utilization and allocation of resources like registers and memory during this phase are crucial. Last but not the least, we have the optimization, where the compiler refines the generated code so that its performance can be enhanced. The type of optimization would include speed optimization, memory usage optimization, and sometimes even power consumption if you're writing code for mobile devices or tablets, etc., or even for embedded systems. The compiler can perform optimization at various levels. It can either be local level within single block of code. It can perform global optimization, transforming overall code or the multiple blocks of code, or even inter-procedural optimization. That means optimization of resources between different functions or between different procedures. Strategies for optimizations include, now this is kind of a part that I added into my slides as a precaution. Dead code elimination, remove parts of code that are not effective, that will not affect the program output, the final output. Loop optimization, enhance the performance of loops, which are often bottlenecked in program execution. Inline expansion, replace function calls with the actual function code when beneficial. A simple example of code optimization is shown here. Original code, if this is the original code, w equals to x plus y and v is equals to x plus y plus z. Now the object code that will be produced would be something like load x, add y, store w. The value will be stored in w, then you would load x, you would load y, you would load x, then you would load and add y, then you would load and add z, and then store the final answer in v. Now looking at this original code, you know very well this part is actually w, because w is equals to x plus y. So what you can do, you can simply load x, you can add y to it, you can store it in w, and then if you simply add z to it, you'll have the final output that is desired, and then you can store it in v. So as you can see, from 1 2 3 4 5 6 7 steps or 7 lines, we reduced it to just 5 lines. This is a very simple example. Sometimes you're able to reduce many 50 60 lines of code when you go through the optimization process. Representing the grammar of a programming language, this is kind of like the second main thing. Again, this is one of the topics which frequently appears in a paper 3. The representation of a programming language is a critical component in computer science. You need to know how you can represent the grammar of a programming language, and I'm talking about on a pen and paper or on computer. There are two methods of this, of representing a grammar of a programming language or syntax of a programming language. In Cambridge A-level syllabus, they are known as syntax diagram and BNF notation. These foundational tools are indispensable. They are very necessary for comprehending the structure and processing of language by translation softwares. So first of all, let's talk about syntax diagrams. They are also known as railroad diagrams. Well, I'm not really sure why they are known as railroad diagrams. They look more like the diagram of a train, maybe. They look like this. They look more like trains, like different bogies are connected together rather than railroads. But hey, I did not came up with this name, so never mind. They offer a visual approach to representing the grammatical rules for a programming language. This design is very essential for understanding how various language elements are constructed. They can have arrows, they can have lines, boxes, and that's about it. They can also have depict tokens, literals, and control structures of a language. But most commonly we use boxes, rectangles, arrows, and lines. They guide the reader through the potential path for creating syntactically valid statements or expressions. Particularly adept at illustrating complex nested grammar rules, making intricate language more digestible or more readable or more understandable. Designing and reading a syntax diagram to create it, break down the language construct into its basic elements and illustrate the permissible paths and structures. To interpret these diagrams, follow the flow of the diagram, means keep on following the arrow, to understand how different language elements combine to form valid constructs. Application in language learning and design, they serve as an excellent tool for teaching basics of programming languages. Well, I don't agree with that, but hey, useful in design phase of new programming languages, yeah, that is absolutely true. If you're trying to come up with a programming language of your own, then you're definitely going to draw a lot of syntax diagrams, because these are very excellent for documenting the structure of programming language. Here is an example image that shows syntax diagram. Assignment statement should be written as how there should be a variable. Now this this rectangle having the word variable means this can be any name. Equals to, like, one variable can be equal to variable operator variable, and that's it. This is terminator, that means you cannot add anything else. So basically in this specific programming language, a variable or a must have a variable, another variable plus an operator plus a variable. And what exactly can be a variable? It can have one letter, or it can have two letters, or it can have three letters. That's it. Having more than three letters or less than one letter is not allowed. So this diagram for a variable tells us that in this programming language, whatever it is, a variable must have at least one letter and a maximum of three letters in its name. And what is the definition of a letter? It can either have A, B, C, or D. It cannot have a fifth character. Whereas an operator is only limited to plus, minus, multiplication, or division. This is how we create syntax diagrams for a programming language. And I've already explained this, but if you want, you can read it yourself as well. Then the next way of representing the grammar of a language is known as BNF form, or Backus-Naur form, or BNF. It is a widely recognized notation technique for defining a programming language's syntax in a formal and precise manner. You can think of BNF and syntax diagram as flowchart and pseudocode. Flowchart is a pictorial form, so is syntax diagram, whereas BNF is more written explanations, such as just like pseudocode, although both of them represent the exact same thing, but the method of representation is different. BNF utilizes a series of symbols and rules to articulate the structure of a language in a concise or summarized way. It includes terminal symbols, actual language tokens, and non-terminal symbols, abstract constructors, or grouping. You'll get to understand what this is. It's okay if you cannot understand these fancy terms. All you need to do is how to convert something is in BNF form and how to read a BNF form. It is based on production rules which specify how non-terminals can be composed of terminals or other non-terminals. Terminals are basically actual programming language symbols, whereas non-terminals are things that are not keywords in a language. Now, how do we construct grammar of a language using BNF? It is based on production rules which specify how terminals can be composed of terminals or other non-terminals. BNF is powerful because it can define rules recursively in form of loops or nested language structures. Now, BNF is very unambiguous, so that's why it's ideal for formal specification of programming languages. Plus, it is widely accepted across the globe. Comparing syntax diagram and BNF, syntax diagrams offer a visual method for grasping language syntax. It can help those who have a better visual understanding of things, whereas BNF provide a more compact, more formal textual representation for those who like to read detailed specifications. Syntax diagrams excel at representing complex structures in a rather easy method. BNF is more efficient to define intricate grammar rules in a summarized form. BNF uses a set of symbols such as less than and greater than symbol is used to enclose an item. Double colon followed by an equal to sign separates an item from its definition. This this vertical bar is between items indicate a choice, like either it can be this or either it can be this. This is terminator at the end of a rule. Example, write the Backus-Naur form for a variable that can only have 5 values, A, B, C, D, or E. So how you will write it? You'll write the word variable, that's your basic encapsulated in greater than less than sign. Then you'll write the I won't really call it assignment operator, but more like a definition symbol, I should say. Then I will write a variable can either be A or B or C or D or E, because this symbol represents a choice. If you have to write BNF form for a variable, so it can be any number of letters. How you can write that? A variable should be equal to a single letter or variable followed by letter. Or you can write it as variable should be equal to or should consist of a letter and a variable. If you write this or you write this, both of them will be considered perfectly acceptable. Whereas if you would want to write it in form of a syntax diagram, I think we already then it can be something like this. Instead of letter, you'll write over here a variable. This is how you'll make the diagram. Every choice in a syntax diagram is kind of like adds one more layer or step to the diagram. Another way, or another thing, or rather I should say in the syllabus, the last thing in chapter number 16 is reverse polish notation, RPN. It is a mathematical and logical notation where operators follow their operands. This notation simplifies the process of parsing. Now this is not a way of representing program grammar. Okay, don't mix it up. Maybe Cambridge examiner should have given a different subheading or some explanation before this, but anyways, this is a way of simplifying the parsing of mathematical expressions. This is used during the parsing stage. This is a way of simplifying the process of parsing and evaluating arithmetic expressions by eliminating, the main aim is to eliminate parentheses, brackets. RPN is also referred to as postfix notation. It reverses the usual arrangement of operators and operand. For example, the traditional expression can be 3 plus 4, and in RPN it would be written as 3 4 plus, not 3 plus 4. Operators are always put onto the you can say right hand side of the numbers or variables. This method greatly simplifies computational logic. How? Well, kind of beats me. As the sequence of operation that was a joke. Please don't be alarmed. As the sequence of operation is inherently defined by the notation itself. Key characteristics, well, operators are placed after the operands. So first of all, you write all the numbers and then you write the operands. RPN removes the need for parenthesis. As the order of the operation is clear from the notation, you solve it from the left hand side and always move towards the right hand side. It simplifies the parsing process for compilers as the structure of RPN expressions is more straightforward. So compilers find it more easy to solve it or to compile it or parse through it. For example, take this expression 5 multiplied by 3 plus 2. In RPN, it should be expressed as 532 plus and then multiplication. Now this would mean that this plus should be applied on these two first, and then the answer should be multiplied with this. These are the operands and these are the operators. Executing the operation in the sequence dictated by RPN is always from left to right. How you would solve it if you're still confused, what you are going to do, first of all, solve whatever is inside the bracket. Okay, I'll show you step by step working. 5 multiplied by 3 plus 2. Let me for a moment just erase everything over here and over here. Now first of all, you'll solve whatever is inside the bracket. So let's leave 5 and the multiplication sign. 3 and 2 in RPN form would be written like this, whereas the parenthesis, there is no parenthesis in RPN, so it will simply vanish. Next, we are going to solve rest of the state. So we already have 3, we already have 2, and we already have a plus. We'll move this at the end of the expression, whereas 5 will remain as it is at its current position, and this will be our final answer. Remember not to move this at the end of this. Okay, that would be wrong. Evaluating an RPN expression. A stack can be used to evaluate an RPN expression. Now how you can do that, the values are added to the stack in turn going from left to right, and whenever an operator is encountered, it is not added to the stack, but it used to operate on the top two values of the stack, which are popped off from the stack first. They are popped off, that operator is applied onto them, and then the value is pushed back onto the stack. The intermediate states of the stack when two values have been popped are not shown. This is repeated until there is a single value on the stack and the end of the expression has been reached. Now this is another type of question that sometimes comes in the Cambridge examination, so I've included an example as well. For example, this is an expression a plus b multiplied by c minus d. If you convert it into RPN, it would become AB plus CD minus and then multiply, as brackets have the highest precedence. Now you'll be given some values like A is 2, B is 3, C is 4, D is 5, and then you'll be given these blank stack diagram, and then you'll be asked to evaluate the expression using RPN. First of all, you'll take the value of A and add it to the stack. Then you'll take the value of B. After constructing an RPN, obviously, you'll move it into the stack, and then whatever is the symbol after it, you'll write at the top of the stack. What will be the answer? 3 plus 2 would be 5. You'll push it back into the next stack diagram. Then you'll add the value of C, and then you'll add the value of D and subtract them together. You can write the minus symbol over here. 5 minus 4 would be -1. So it will be -1 and 5. Now you apply the multiplication symbol. 5 multiplied by -1. The last stack would hold the final answer, that is -5. This is basically the explanation. If you want to read it, a written explanation, you can pause and go ahead. I've already explained it to you. And well, here goes this again, some more points of explaining how it went. The last, again, remember, the last two values in stack will be popped, multiplied together, and answer will be pushed back. This completes the evaluation, as no more operators or variables are left in the RPN. So basically, in paper, you'll be given an expression, you'll be given values for it, and then you'll be given a blank stack diagram. Let me show you an example. Something like this will be given to you, a blank diagram consisting of multiple stacks along with the expression and some supposed values for the variables. So first of all, you'll need to convert it in RPN, and then you can use this blank stack diagram in order to solve and evaluate your expression. And that's absolutely everything you need to learn, you need to know for your chapter number 16, specifically 16.2. I hope you have understood everything. Feel free to leave your comments below so I know how well or how bad I'm doing. Do give this video a thumbs up if you like it, and share it with your friends. I'll see you guys in the next video. Till then, take care. Allah Hafiz.